We can't solve the three-body problem with a single equation, but we can fight chaos with calculation. In the quiet hum of data centers around the world, thousands of processors run day and night, not mining cryptocurrency or streaming videos, but replaying the birth of star systems, the death spirals of black holes, the gravitational tango of three suns locked in an eternal embrace. These are not guesses. They are numerical integrations. Step-by-step reconstructions of Newton's laws, computed with such precision that each tiny gravitational tug is accounted for, 1 femtosecond at a time. This is how we navigate the unsolvable. The method is deceptively simple. Start with the positions, masses, and velocities of three bodies. Calculate the gravitational force between each pair. Use that force to nudge their positions forward by a minuscule amount of time, a billionth of a second perhaps. Repeat again, again, again. Do this billions of times, and you trace a path through space-time that, while not exact, is as close to reality as our machines allow. But even this brute force approach has limits, because chaos doesn't care how powerful your computer is. It only cares about precision. Every number in a simulation is stored with finite digits, 16, 32, 64 bits of information. That means every position, every velocity carries a tiny rounding error. In a stable system, those errors stay small. But in a chaotic three-body system, they grow exponentially. Just like in the real universe, a difference smaller than the width of a proton can, over millions of steps, balloon into a completely different outcome. So, no simulation is truly predictive over infinite time. It's a forecast with an expiration date, like a weather model that's accurate for 10 days. Then dissolves into noise, yet scientists have learned to work within these bounds. Instead of asking, what will happen? They ask, what could happen? They run. Thousands, sometimes millions of simulations, each with slightly different starting conditions, creating a statistical map of possible futures. This is called an ensemble simulation. From it, they extract probabilities. A 70% chance of ejection within a million years, a 5% chance of a stable planetary orbit, a 1 in 10,000 chance of a perfect figure-8 dance. This approach has revealed astonishing patterns. In 2018, a team led by astrophysicist Nicholas Stone ran over 1 million three-body simulations and discovered that chaotic systems often follow a universal statistical law, regardless of the masses or initial speeds. The time it takes for one body to be ejected follows a predictable distribution. The energy exchange during close encounters clusters around certain values. Even in randomness, there is rhythm. More recently, machine learning has entered the arena. In 2020, researchers trained a neural network on millions of three-body simulations. The AI didn't learn the physics, it learned the outcomes. Given a set of starting conditions, it could predict the final state, ejection times, orbital parameters, collision probabilities, orders of magnitude faster than traditional simulations, with surprising accuracy. Critics warned, this is interpolation, not understanding. The AI is a black box, mimicking patterns without grasping why they exist, and they're right. But in a problem where exact understanding is impossible, approximation becomes wisdom. Still, simulations are only as good as the physics we feed them. Newtonian gravity works beautifully for most stellar systems. But when objects get extremely close, like black holes or neutron stars, or when velocities approach the speed of light, Einstein's general relativity must take over. And simulating three bodies in full general relativity. That's at the bleeding edge of computational astrophysics. Only a handful of supercomputers can do it, and even then, for short durations. Yet these efforts are crucial. They helped interpret the gravitational wave signal from the black hole merger GW1 90521, a system so massive and fast-spinning that Newtonian physics would have gotten it completely wrong. The three-body problem, it turns out, isn't just about stars. It's woven into the fabric of space-time itself, and simulations have practical uses beyond theory. When NASA plans a mission to Jupiter's moons, engineers run three-body models of the Sun, Earth-Jupiter system to find low-energy pathways. When astronomers search for exoplanets in triple-star systems, they simulate thousands of orbital configurations to see which ones would produce the observed light curves. Even the trajectories of space junk in Earth orbit must account for the moon's and sun's gravity, making low Earth orbit a subtle three-body problem. But perhaps the most profound use of simulation is philosophical. By watching thousands of virtual triple systems unfold, some serene, some violent, some beautiful, we confront the sheer diversity of cosmic possibility. We see that stability is rare, but not miraculous, that chaos is common, but not absolute, that the universe is not biased toward order or disorder. It simply explores every path allowed by its laws, and in that exploration, we find humility. Because every simulation ends with a reminder, this is not the real system. It is a shadow, a proxy, a best guess. The true three-body problem plays out in the void, beyond our reach, governed by laws we understand but cannot fully command. We simulate not to conquer chaos, but to converse with it. And in that conversation, we learn to listen. In the next chapter, we step back from three bodies and look at the bigger picture, because the universe rarely deals in threes. It deals in thousands, millions, billions. And when you scale up, the problem doesn't get simpler. It becomes something else entirely. Three bodies are enough to break predictability. But the cosmos rarely stops at three. Look beyond the quiet hierarchies of Alpha Centauri or the choreographed loops of theoretical models, and you'll find star clusters where hundreds of suns swarm like bees in a hive, each tugging on every other in a gravitational free-for-all. Venture further, and you encounter globular clusters, dense spheres of 1 million stars orbiting galactic cores, their motions so entangled that no single path can be traced for long. And then there are galaxies themselves, spirals like our Milky Way, home to 200 billion stars, swirling in a dark sea of invisible matter, their collective dance governed by gravity on a scale Newton never imagined. This is the n-body problem, where n is not three, but thousands, millions, even trillions. And it is the true face of cosmic complexity. Unlike the three-body problem, which is chaotic but solvable step by step, the n-body problem is computationally monstrous. The number of gravitational interactions grows with the square of n. For three bodies, that's three pairwise forces. For 1,000 stars, it's nearly 500,000. For a galaxy, quadrillions. Every moment, every second, across billions of years. No computer, no matter how powerful, can calculate all those forces exactly for a real galaxy. So, astrophysicists use clever approximations. They group distant stars into smooth gravitational fields, simulate only the most massive objects in detail, or use statistical models that treat stars like molecules in a gas. These methods work astonishingly well. They've helped us map dark matter, predict galactic collisions, and understand how spiral arms form and fade. but they also remind us of a deeper truth. The universe is not just unpredictable in detail, it is fundamentally unknowable in its entirety. Even if we had a computer the size of a planet, even if we knew the exact position and velocity of every star, gas cloud, and black hole in the Milky Way, chaos would still win in the end. Because, in a system with millions of interacting bodies, sensitivity to initial conditions isn't a curiosity, it's the rule. A single supernova, a rogue planet, a passing dwarf galaxy, any tiny perturbation can ripple through the system, altering the fate of stars thousands of light years away over cosmic time. This doesn't mean the universe is random. On large scales, gravity imposes order. Galaxies rotate, clusters merge, cosmic webs form. But that order emerges from chaos, not in spite of it. It's statistical, not deterministic. We can say with confidence that the Andromeda Galaxy will collide with the Milky Way in about 4 billion years. But we cannot say whether our solar system will be flung into intergalactic space or remain nestled in the new merged galaxy's suburbs. And that's okay. Because the beauty of the cosmos isn't in its predictability, but in its layered complexity, where simple rules give rise to endless variety. Newton's law of gravity is just one line of math, yet from it springs binary stars, triple systems, star clusters, galaxies, and the vast cosmic web that stretches across the observable universe. The three-body problem is the gateway to this realization. It shows us that even the simplest addition beyond 2 introduces irreducible uncertainty. And if 3 bodies can do that, what hope do we have with billions? But here's the wonder. We don't need to know everything to understand something. We don't need to track every star in a cluster to know how it evolves. We don't need to simulate every atom in a planet to understand its climate. Science thrives not on total knowledge, but on effective knowledge. Models that capture the essence of a system without replicating every detail. And in that spirit, the three-body problem becomes more than a puzzle. It becomes a metaphor. For life is an n-body problem too. Every decision we make is influenced by countless factors: genetics, environment, chance encounters, the gravitational pull of other people's choices. We cannot predict our own futures with certainty. Yet we find patterns. We build relationships. We create meaning. The universe, it seems, operates the same way. It doesn't demand that we solve everything. It invites us to explore, to approximate, to marvel at the dance, even when we can't predict the next step. In the final chapter, we return to where we began, not to the stars, but to ourselves, to what the three-body problem teaches us about knowledge, humility, and the human desire to find order in a chaotic sky. We began this journey with a feeling, the quiet trust that the sky above us is orderly, dependable, a mirror of reason. That trust gave us calendars, navigation, science itself. But the three-body problem shattered that illusion, not with violence, but with a whisper. You cannot know everything, even when the rules are clear. And yet, rather than leaving us adrift, that revelation offers something deeper, humility wrapped in wonder. Because the three-body problem is not a failure of human intelligence. It is a feature of the universe, a boundary where certainty ends and mystery begins. And standing at that boundary is not a defeat. It is an invitation. For centuries, we believed that to understand the cosmos meant to control it, to reduce it to equations we could solve, to futures we could foresee. Newton's clockwork universe promised that if we knew the present perfectly, the future would unfold like a scroll. But Poincaré showed us the scroll is written in invisible ink, legible only for a while, then fading into fog. This is not a limitation of science, it is a refinement of it. Science does not require omniscience to be powerful. It thrives on partial knowledge, on models that work well enough, on predictions that hold for now. We send rovers to Mars not because we've solved the solar system's N-body problem exactly, but because we've approximated it with astonishing precision. We detect black hole mergers not by foreseeing them, but by listening for their echoes in space-time. The three-body problem teaches us that knowledge and control are not the same thing. We can understand gravity deeply, its laws, its symmetries, its consequences, without being able to predict every outcome. And that's not weakness, it's maturity. Think of a river. We understand fluid dynamics. We know how water flows around rocks, how turbulence forms, how erosion shapes landscapes. But we cannot predict the exact path of a single leaf dropped into the current. Does that mean we don't understand rivers? No. It means rivers are complex systems, governed by laws, yet full of emergent beauty that resists total prediction. So too with the stars. The three-body problem reminds us that the universe is not a machine to be mastered, but a conversation to be joined. We ask questions. The cosmos answers, not always clearly, not always completely, but always honestly. And in that exchange, we grow. This has profound implications for how we see ourselves. In a perfectly predictable universe, free will seems illusory. If every atom's motion is determined from the Big Bang, are we just clockwork ghosts? But in a chaotic universe, one where tiny uncertainties amplify into vast consequences, the future is open in a deeper sense, not random but unwritten, not predetermined but shaped by the interplay of law and chance, necessity and accident. We are part of that interplay. Our choices matter, not because they defy physics, but because they participate in it. A kind word, a scientific insight, a decision to explore rather than conquer, these are like the butterfly's wing flap in a chaotic system. Their full consequences may be unknowable, but their potential is infinite. And perhaps that's the greatest lesson of the three-body problem, that uncertainty is not the enemy of meaning. It is its birthplace. If everything was certain, life would be a script. But because the future is unwritten, even in a universe of ironclad laws, every moment carries possibility. Every orbit, every collision, every stable dance in the cosmic storm is a testament to the fact that order can emerge from chaos, not by erasing it, but by dancing within it. We see this in our own lives. Relationships are three-body problems, sometimes more. Parent, child, partner, friend, rival, mentor. The dynamics shift with every word, every silence. There is no formula for love, for trust, for reconciliation. Yet we navigate them anyway, not with perfect foresight, but with care, attention, and hope. The cosmos mirrors us, and we mirror the cosmos. So when we look up at the night sky now, we see more than points of light. We see stories of stars flung into the void, of planets born in tilted disks, of gravitational choreographies that last billions of years. We see both fragility and resilience, both chaos and grace. And we realize that the three-body problem is not just about stars, it's about us. It's about the courage to seek knowledge even when the answers are incomplete. It's about the wisdom to act with care in a world where small choices ripple outward. It's about the awe that comes not from having all the answers, but from standing beneath a sky that still holds mysteries after all these centuries. In the end, the universe does not owe us predictability, but it offers something richer, a dance we can join, even if we can't see all the steps. And in that dance, in the tension between law and chaos, between knowing and wondering, we find not despair, but belonging. Because to be human is to live in the space between certainty and mystery. To be human is to build telescopes, write equations, tell stories, not to conquer the unknown, but to say with quiet reverence, we are here, we are listening, and we are part of this. The three-body problem remains unsolved in its full generality, and perhaps it always will. But in that unsolved space, we find room to grow, to imagine, to hope. And that, perhaps, is the most beautiful solution of all.